Hello, and welcome to this video series on algorithms. This is part 10 of Module 4 on greedy algorithms. In this section, we will study the optimal caching problem. Let's briefly review the memory hierarchy to motivate the optimal caching problem. The CPU first requests data from the cache. The cache is small but provides very fast access. If the requested data is not in the cache, it must be fetched from main memory or disk. These storages are much larger, but have significantly slower access times. For example, when the CPU requests data item A, if it is already stored in the cache, the data is returned immediately, incurring only a very small delay. This situation is called a cache hit. In contrast, if the CPU requests data item X and it is not in the cache, the data must be fetched from main memory or disk. This situation is called a cache miss. When a cache miss occurs, the requested data must be fetched from memory or disk, which causes a significant delay. Afterward, the new data is stored in the cache, so it can be accessed quickly in the future. To make room for this data, an existing data item must be removed from the cache. For example, we may evict data item D to make space for the new data X. The rule used to decide which data item to remove is called the eviction plan. Note that the eviction policy directly affects the cache miss rate. For example, after evicting data item D, the CPU may soon request D, causing another cache miss. If we had evicted data item A instead, that cache miss would not occur. This leads to a natural optimization problem. Design an eviction policy that minimizes the number of cache misses. Fewer misses mean fewer expensive transfers from memory or disk, which reduces total execution time. Formally, let U be a set of M distinct data items stored in memory. For a given program, we are given the complete access sequence D, which lists the items requested over time. For example, D equals U5, U2, U5 means that the program requests U5, then U2, and finally U5 again. Given a cache that can hold K items, where K is smaller than M, our goal is to choose an eviction plan that minimizes the number of cache misses over the sequence D. Intuitively, to minimize the total number of cache misses, we should delay future misses as much as possible. When a miss forces an eviction, a natural choice is to remove the item whose next access is farthest in the future. Evicting this item postpones the next cache miss, likely reducing the overall miss rate. This greedy idea leads to the farthest-in-future eviction plan. For example, consider the data access sequence shown in the table. From the sequence, we can determine the next access time of each cached item. Data A is accessed first, D second, C third, E fifth, and B sixth. Since data B will be accessed farthest in the future, the greedy policy evicts B. Next, We prove that this strategy minimizes the number of cache misses. We will show that the greedy farthest-in-future policy never produces more cache misses than an optimal eviction policy. First, we define a reduced schedule. A reduced schedule is an eviction plan that removes data from the cache only when a cache miss occurs. That is, only when space is needed for newly fetched data. Know that the farthest-in-future strategy always produces a reduced schedule. Proposition 1 states an important property. For any eviction plan S, we can convert it into a reduced schedule SR and incur no more cache misses. To see why, observe that SR delays any eviction in S until the next cache miss, when an eviction is actually required. Since no cache miss occurs between the original eviction in S and the delayed eviction in SR, delaying the eviction cannot increase the number of cache misses. Therefore, SR incurs no more cache misses than S. We will use this proposition when proving the correctness of the greedy strategy. Proposition 2 compares two eviction plans, an arbitrary plan S and the greedy farthest-in-future plan SFF. It states that if S and SFF make the same eviction decisions for the first J data requests, then there exists a reduced schedule S prime that first makes the same eviction decision as SFF on the J+1th request, and second, incurs no more cache misses than S. This proposition shows that we can modify any eviction plan to agree with the greedy choice at the next step without increasing the number of cache misses. First, because S and SFF make the same eviction decisions for the first J requests, they have the same cache contents just before the J+1th data request. Now, consider the J+1th request. If it is a cache hit, no eviction occurs, and the cache contents of S and SFF remain identical. In this case, we define S prime by copying all eviction decisions from S starting at the J+2th request. If it is a cache miss, and S and SFF evict the same item, their cache contents are again identical after the request. We can define S prime in the same way by copying from S. The remaining case is when the J+1th request causes a cache miss and S and SFF choose different items to evict. Let the requested item at the J+1th step be D. On this cache miss, let schedule S evict item F, while the farthest-in-future schedule SFF evicts item E. The table at the bottom of the slide shows the resulting cache content under S and SFF, respectively. Now, consider the next cache miss. Note that this miss does not have to occur at request J+2. It may happen later. When there are no cache misses, S prime does nothing. When the next miss occurs, the requested data cannot be E. Since SFF evicted E, E is the item whose next use is farthest in the future. Therefore, Some other request must trigger this cache miss. This leaves two cases. The requested data is F, or it is some G that is neither F nor E. Now, we analyze what happens at the next cache miss. Depending on the requested item and the evasion choice made by S, there are four cases. First, the requested data is F, and S evicts E. Second, the requested data is G, and S evicts E. Third, the requested data is F, and S evicts some data H that is not E. Fourth, the requested data is G, and S evicts some data H that is not E. In the fourth case, the decision of S does not involve E or F, which are the only items that differ between the cache states of S and SFF. Therefore, we can let S prime make the same evasion decision as S in this case, without causing more cache misses than S. We now focus on the first three cases, where S prime cannot be defined by simply copying from the decisions made by S. Consider the first case, where the missed data is F and S evicts E. Since F is already in the cache content under SFF, S prime does nothing at this step. In contrast, S incurs a cache miss on F. Therefore, up to this point, S prime has no more cache misses than S. After this request, the cache content under S and SFF plus S prime become identical. From then on, we define S prime to follow the same evasion decisions as S, which will not increase the number of cache misses relative to S. Now, consider case 2, where the missed data is G and S evicts E. On this request, both S and S prime incur a cache miss for G. To make the cache contents match after servicing this miss, we define S prime to evict F. With this choice, both schedules have one cache miss at this step. So, S prime does not incur more misses than S. Afterward, the cache contents of S and SFF plus S prime become identical. From then on, we can let S prime copy the remaining evasion decisions of S, which will not cause more cache misses than S. Then, consider case 3, where the missed data item is F and S evicts some data H that is not E. Under S, requested F is a cache miss. Under SFF, F is already in the cache, so this request is a cache hit. However, to make the cache contents match after this point, we let S prime remove H and bring E into the cache. After this step, the cache contents of S and SFF plus S prime become identical. From then on, we can define S prime by copying the remaining division decisions of S, without causing more cache misses than S. Note that this step makes S prime temporarily non-reduced, because it changes the cache content even though the request to F was a cache hit. However, by proposition 1, we can convert any non-reduced schedule into an equivalent reduced schedule without increasing the number of cache misses. So we can replace S prime with its reduced form and preserve the same cache miss count. Putting these cases together proves proposition 2. Finally, we prove the optimality of the greedy strategy by induction. Recall proposition 2. If a schedule S and SFF agree on the first J requests, then we can construct a schedule S prime that agrees with SFF on the J+1th request and causes no more cache misses than S. For the base case, J equals 0, let S be an optimal schedule. By proposition 2, we can construct a schedule S prime that shares the first decision with SFF and incurs no more cache misses than the optimal schedule S. Since S is optimal, S prime is also optimal. Denote this schedule as S0. Note that S0 agrees with SFF on the first decision. For the next step, set J equals 1 and let S equals S0. Since S0 is optimal and already agrees with SFF on the first request, proposition 2 implies that we can construct another schedule S1 that is both optimal and agrees with SFF on the first two evasion decisions. We can repeat this argument for J equals 0, 1, 2, and so on, until we reach the end of the access sequence. At each step, proposition 2 let us transform an optimal schedule into another optimal schedule that agrees with SFF on one additional request. After processing the entire sequence, we obtain an optimal schedule that agrees with SFF on every evasion decision. Therefore, SFF itself is optimal. We can implement the farthest-in-future policy efficiently using a heap. Given the access sequence shown as the yellow table, we first scan it to build a linked list for each data item, which is shown as the white table. Each list stores the future times when the item will be accessed. We then maintain a max heap keyed by each cached item's next access time. With this key, the item whose next use is farthest in the future is at the top of the heap. In case of a cache miss, we can evict the heap maximum and insert the requested item with its next access time. In case of a cache hit, we advance that item's pointer to its next node in the linked list. Then update its key in the heap. In both cases, the next access time of an item is obtained by moving to the next node in its linked list. Let n be the total number of data requests, and let k be the cache capacity. The heap stores only the items currently in the cache, so its size is at most k. Each request triggers a constant number of heap operations, including delete, insert, or key update. Each of such operations takes O log k time. Over n requests, the total running time is therefore O n log k. Thank you for watching, and see you next time.